캐비테이션의 인맥 특성 연구에 대해서 중남대학교의 에슈라프 회원님께서 발표해 주시겠습니다. You can start when you're ready. Okay. I think presenter is not available.
Use the laptop. Use the laptop.
Hello everyone, good afternoon. This is Sandy Ashraful Haq, Master's student from Jeju National University. Today I am representing flow-induced noise and cavitation control laboratory under the Department of Autonomous Vehicle System Engineering, and my topic is to present a study on the effects of dissolved gas content on the critical characteristics of bubble cavitation. Let's begin from the beginning. So here is my discussion contents. In the discussion contents, first I will say what motivates us for this research, and then I will show the two previous works which are quite related about our recent work, and then I will show the experimental apparatus of ours, and finally I will discuss the key outcomes of what we find. So, for engineers, cavitation means noise generation, vibration, performance erosion, and material degradation, making its control and prediction critical for many engineering applications. The dissolved air content in water directly influences the number and size distribution of bubble. So, from the left figure, we can see that due to the impact of bubble cavitation, propeller affects significantly. So that this is the reason of bubble cavitation, that the effect of bubble cavitation for a propeller, it affects significantly. And the right to high speed visualization videos, it shows that at a fixed flow velocity, the flow velocity is fixed at 10.5 meter per second, but the difference between the two dissolved content 4.5 and 9.2, we can see a noticeable significant difference between the two dissolved gas content, even if the flow velocity is fixed. So, in this study, our objective is the influence of dissolved gas content on the critical characteristics of bubble cavitation to improve cavitation prediction in marine hydrodynamic model testing. Here the first one was presented at 21st Symposium on Naval Hydrodynamics, where they have showed the relation between the tension of the water and the number of nuclei distribution, and also showed us that the deep vortex is moderately affected, whereas the bed surface, it has negligible effect, and the bubble cavitation has significant effect. And the lower one is from Journal of Fluid Mechanics. Here the left figure shows that the traveling cavitation bubble undergo highly asymmetric collapse, and bubble deformation is strongly influenced by the separated boundary layer flow, and the collapse of bubbles, it is not symmetric as the spherical bubble theory. And the right figure shows the relationship between the bubble maximum size distribution and the cavitation event rate. It is not directly proportional. The cavitation event rate differs significantly with the bubble size distribution. So, the free stream nuclei distribution affects significantly on cavitation. So, this is our Jeju National University cavitation tunnel. Our flow speed is 20 meter per second, and we can go up to 30 meter per second if we want. our pressure range is 10 to 300 kilopascal. And how we control the dissolved gas content in our cavitation tunnel? Actually, water is circulating from the water tank to the degas tank. And by using the vacuum degasification system, we control our preferred dissolved gas content, where the water diffuses into the vapor phase and promotes the dissolved gas molecules into that vapor phase, and thus the system pressure reduces the atmospheric pressure, and that's how we can control the dissolved gas content in our water tunnel. Here the left image, it is taken while we are conducting the experiment, and this is the bubble cavitation I am talking about. Our test section hydrofoil model is NACA 0012, and the dimension of the hydrofoil is 100 by 100 millimeter. And we have used high speed visualization camera for this experiment, and also the LED illumination system. Our test section length is 1.4 meter in length, and area of the dimensions are 100 by 100 millimeter. The hydrofoil is mounted at 3 degree angle of attack, and this is our velocity range, and our DO content range was 4.5 to 10 measured as parts per million. So I have mentioned already that we have measured the dissolved gas content as ppm. So here is the relation between the ppm and the dissolved oxygen concentration, where 1 ppm corresponds to 1 times 10 to the power minus 3 kg per cubic meter, and the right one shows the optical biosensor. So why we use the optical biosensor instead of the polarized sensor? Because optical biosensor measurement response is 6 times faster and more accurate, and the right one shows the schematic of how this sensor works. So if I explain shortly, the optical fiber in the sensor emits the blue light and causing the sensing element to glow or luminescent diode. And the sensor cap contains the diffusion layer, where the oxygen is constantly moving through the diffusion layer and interact with this luminescent diode. And this effect is called quenching. Finally, the photodetector compares this luminescent diode with the reference LED, and allowing us to measure the dissolved oxygen concentration in the water. So actually this is our previous study. Previously we had did the inception and desinence of deep vortex cavitation, and we have seen the dissolved gas effect of deep vortex cavitation by using an elliptical NACA 1600203D hydrofoil. So we have seen that if we divide the deep vortex system, we have seen that it shows different sensitivity. The first one is intermittent deep vortex cavitation, and the second one is attached deep vortex cavitation. And what does it mean by intermittent deep vortex cavitation? The first uppermost figure, that is the condition of intermittent deep vortex cavitation, and as the pressure goes down, we find the attached deep vortex cavitation inception, and as it goes on, we find the deep region sheet cavity, leading edge sheet cavity, cloud cavity, and fully developed cloud cavity. So the lower two figures, if we normalize our tested highest DO condition, I mean 10 ppm, we find the different sensitivity of deep vortex cavitation, where intermittent deep vortex cavitation shows the highest sensitivity with respect to dissolved gas content, but attached deep vortex cavitation, it shows the less sensitivity in both inception and desinence cases. That is actually one of our main novelty in this previous study. So let's go to the result section. So this slide represents the bubble cavitation mechanism within approximately 7.5 milliseconds. Within approximately 7.5 milliseconds, this slide explains the complete transient bubble cavitation and only one cavitation event. So when cavity inserted in a vortex system, we know that cavitation inception appears from the pre-existing nuclei clusters. I'm sorry, actually I don't know why this shows something like that. So the cavitation appears from the pre-existing nuclei cluster, and when the vortex core is strong enough and air nuclei entering into that vortex system, cavity incepted. After inception of bubble cavitation, bubble absorbs the residual vapor, and thus the area of the bubble increases, and after that vapor dissipates and it started to deform. So actually this is the stage that the collapse of the bubble goes to the asymmetry. So at the deformation, after the deformation stage, vapor started to dissipate and gradually disappeared, and bubble goes to fragmented into smaller bubbles. So that is the process of fission. Before collapse, we found the two processes, fission and rebound. And the right schematic shows that how a single cavitation bubble inception to collapse process. So this slide shows us the bubble cavitation inception with respect to different dissolved gas oxygen condition using top view visualization and side view visualization, and also the inception and desinence condition. So as DO increases from 4.5 to 10 ppm, the cavitation number increases. We know that at the lowest DO condition, the nuclear population remains relatively small. So the cavitation number is lower, and as DO increases, cavitation number becomes increases, and shows us that the effect of dissolved gas content on the bubble cavitation. And by inception, this is the condition we mean as inception, and desinence means that there are no cavity in that vortex system. So this slide represents the bubble cavitation, inception, desinence, and the relative sensitivity with respect to DO. If we normalize each DO content at our highest DO condition, I mean 10 ppm, then we find that the lowest DO content, 4.5, it shows the highest sensitivity. Why? Because at the lowest DO condition, there the population of nuclei is limited. That's why the sensitivity of DO is higher. But as the DO content increases from 4.5 to 6.2, 8.2 and 9.2, the sensitivity of DO continuously decreasing. And it goes same for the desinence cases also. There is a difference between the inception and desinence. That is, desinence is always higher than inception. And we know already that this is the hysteresis effect, that as when cavity incepted in a vortex system, to remove that cavity from that vortex system, it requires higher velocity. That's why desinence is always higher than inception, and this effect is known as hysteresis. And if we see that inception sensitivity decreases beyond 6.2 ppm, after that it decreases excessively. And 8.2 ppm desinence shows strong DO dependence due to cavity persistence and gas diffusion. So we have performed proper orthogonal decomposition or POD analysis. This slide represents the complete methodology of proper orthogonal decomposition used to analyze the bubble cavitation using high-speed visualization images. So we have the time-dependent cavitation field where xy represents the spatial coordinates, and we have selected the region of interest to physically meaningful cavitation structure only, and each grayscale is converted to the data vector where it represents the number of pixels and n represents the number of snapshots. The mean cavitation field represents the average cavitation current structure and the time average bubble cavitation. The fluctuation cavitation field removes the stationary background and allows us the physically meaningful POD methodology. And POD has been done by using singular value decomposition, where U represents the spatial POD modes, sigma represents the singular values, and transpose of V represents the temporal coefficient. Where spatial POD modes, from spatial POD modes we find the dominant bubble structure, current cavitation patterns and location, and from the temporal coefficient we find the time evolution of each mode and the bubble oscillation behavior. So this slide represents the cumulative energy spectrum of 4 dissolved gas content condition, 4.5 to 9.2. So if we see that at the lowest DO condition, it requires 180 mode to reconstruct the 97% of the cumulative energy. But as the DO content increases, the number of mode becomes increases. Why? Because at the lowest DO condition, the availability of nuclei is limited. But as the dissolved gas content increases, the availability of nuclei is increasing continuously. That's why if we reconstruct the total cumulative energy, we need more mode. So at the highest 9.2 condition, it requires almost 690 mode to reconstruct the total cumulative energy. And this is the temporal evolution of the POD coefficients. We can see what does it mean, the P subscript K. It represents how strongly each POD analyzes how strongly the cavitation appears at each mode. So we can see at 4.5 ppm there are less current structure, but at 9.2 DO content the cavitation becomes strongly irregular and chaotic. That's why the temporal coefficient shows something like that graph. And at fixed condition 0.92, this is for 4.5 DO content. Here mode 1 represents the highest energetically cavitation region, and mode 2 represents the secondary oscillatory region, and mode 3, mode 4 represents the less current cavitation region. So higher order fluctuations are relatively weak at the lowest DO condition. So bubble motion is comparatively stable and organized at the lowest DO condition. But as the DO content increases, the secondary fluctuation structures becomes more stronger because of the availability of nuclei, and the bubble interaction and temporal oscillation increases. As the DO content increases to 8.2 ppm, energy is spread significantly into higher POD modes, and strongly intermittent and distributed fluctuations appear, as we have seen from the temporal coefficient. And at the highest DO condition, 9.2, we can see that the cavitation becomes highly irregular and chaotic, and current low order structures weaken significantly. And we have seen from the cumulative energy distribution that it requires 690 modes. So the mode number, we require more mode number to reconstruct the total cumulative energy. That's why here mode 4 also shows the cavitation that is extremely intensive. That is the highest spatial and temporal cavitation complexity was observed at the highest DO condition. So our conclusion is the DO content, the dissolved gas content or the DO, strongly influences the inception, evolution and the collapse dynamics of the bubble cavitation. And as the DO content increases, it promotes stronger, wider and more persistent cavitation structure. The cavitation behavior transitions from relatively current and localized structures at the low DO, but at the highest DO condition, we find more distributed, intermittent and multi-scale fluctuations. And as we have performed the POD analysis, POD analysis shows us that increasing DO transfers the fluctuation energy from the dominant low order modes to higher order modes. And also the temporal coefficient analysis shows us that the highest DO condition produce stronger intermittent multi-mode oscillation and chaotic cavitation dynamics. Thank you everyone. Thank you for your attention.
네. 그 질문 있으시면 질문 해주십시오. 네.
Thank you for your presentation. I have a question about the POD analysis video. You picked the sigma as the 0.92 and you compare the four different view conditions. Then how about if you consider the same view condition and cavitation number differences, and also if you compare at the inception cavitation number at different view condition, then what result will come?
Okay,
Yeah.
thank you for your question. So here I have compared 0.90 sigma condition with 4 zero content. So 0.92, this is the cavitation inception condition at 4.5. So I have compared the inception condition with the other zero content cases. That's why we can see that there are more modes required at the highest zero condition. And for the lowest zero condition, I mean the inception cases, the modes number are less. That is the analysis of purity. And yes, you are right that we can also do the purity analysis at fixed geo and different conditions. But in this work, our motive is to show the dissolved gas content effects, not the cavity, not the pressure reduction or something else. So that's why I have chosen the cavitation number. At what condition we found the bubble cavitation inception.
또 다른 질문 있으십니까? 없으십니까? 질문 없으세요?
Open the PPT.
Lunch, and you're heading for something like we use relative humidity and absolute humidity to measure something, right? So we use cavitation numbers whether it happens or not, right? And you add another analysis, a point of view of DO as another way of looking at it, addition to it. So this is you're heading for the development of cavitation number 2, which act as another role to be used as criteria for the cavitation.
Yes, Professor. It's possible that to compare another cavitation number and the 4 zero content, but due to the complexity of time, so that's why I have showed here only the one condition.
Good
But
question.
it will make also difference if we compare. Suppose for example, if we take the cavitation number as 1 and take in the 4 zero content for comparing the dissolved gas content effects, we also see the same difference. But due to the complexity of time, so that's why I showed here just for only one cases.
Okay, so where is research heading towards?
The goal.
What's that goal of analyzing the DO and cavitation?
He didn't get the question actually.
As I have showed in the motivation part, that is from our previous condition, previous result. So here if we see that at the lowest level 4.5, the bubble cavitation appears randomly. Just for a few
Can I
cases,
answer that?
but at the 9.2 DO condition,
Okay,
we
yes.
found that the
I think he didn't get the point.
more randomly and more localized, and it affects actually significantly at the highest DO condition.
So another measurement of the randomness.
Yes, Professor.
No, actually, the goal of this
Different,
study,
different.
why we
Did this.
decrease the DO,
Yeah.
yeah? Why we tested these experiments?
To show the effect of dissolved gas content.
Why we need to check it? Why we need to check it?
Model.
Because if we know, we can predict that whether cavitation appears
No.
or when it falls.
No.
Model testing.
Model test, it's a model test. Usually, model test is conducted in,
Lower gate.
it's the 10 ppm cases,
Right, Professor.
right? Or the 5 ppm cases. But so as you showed, the bubble cavitation is strongly affected by ppm,
Yeah, yes, Professor.
right? So it is important, so we need to, so we need to, so check the ppm when we tested the bubble cavitation. 여기 그냥 조금 더 부연 설명을 드리면 버블 캐비테이션은 저기서 보는 것처럼 9ppm에서 실험하는 것과 5ppm에서 실험하는 것은 굉장히 차이가 크기 때문에 사실은 그래서 대부분의 모형 시험 시설들이 DO를 크게를 조절을 하지는 않고 실험을 하고 있습니다. 그런데 여기서 보시면 한 캐비테이션 넘버는 하나 치자면 2배 이상이 차이가 나다 보니까 특히 버블성 캐비테이션들은 더 그렇습니다. 그래서 아직은 표준화되어 있는 DO의 농도에 대한 표준화는 되어 있지는 않은데 그게 이제 약간의 노하우로 각 모형 시험 기관들마다 그래서 상이한 결과들을 주고 있죠. 저거에 대해서. 그래서 그거를 이제 정량적으로 평가하는 일환으로 시험을 하는 거예요.
제가 처음에 질문했던 이제 뭐 원래 실험할 때 캐비테이션 넘버를 조절해가지고
네.
실제 환경과 비슷하게 맞추는 작업을
맞습니다.
하잖아요.
네.
근데 ppm까지 조절해서 그게 그 환경에서 실험됐다라는 예를 들면 실험 결과 이 캐비테이션 넘버가
맞습니다.
얼마였다라고 적으면
네.
ppm도 얼마였다 적는다는 게 개념적으로 제가 두 번째 캐비테이션 넘버 그러니까 그 재현을 했을 때 여러분 이 상황에서 표현할 수 있는 어떤 지수를 만들려고 하는 게
그게 필요한 거고 보통의 이제 저런 캐비테이션 실험 논문들은 그냥 이 캐비테이션 넘버에서 실험을 수행됐다라고 하는 거죠. 그게 이제 DO에 대한 영향을 많이 안 받는다는 차원에서 물론 받는다는 걸 인지는 하고 있는데 그럼 얼마만큼 받아야지 되느냐 그러면 이제 결국은 실험을 할 때는 DO 몇 % 이하에서 해야지 된다라는 표준화가 필요하다고 저는 이제 특히 버블성 캐비티 같은 경우 그게 필요하죠.
랜덤리스는 뭐 부연적으로 분석도 의미가 있는 분석인 것 같긴 한데요.
랜덤리스
목적은 아니에요.
네, 되죠.
결국 아까 기호에 따라서 랜덤리스가 뭔가 패턴이 다르게 나타나는 거가 결론적으로 나온 거죠.
결론적으로 나왔다기보다도 이제 저거는 버블성 캐비티가 최초로 시작되는 포인트 정도입니다. 그래서 버블을 보시면 저게 이제 랜덤하게 발생할 수밖에 없는데 버블성 캐비티는 거기 이제 녹아 있는 뉴클리아이들의 분포 특성 때문에 이제 저렇게 생기는 건데 결국은 이제 저 해당 ppm에서 저런 랜덤하게 발생하는 버블들이 얼마만큼 정량적으로 나왔는지를 보여줘야지만 되다 보니까 그 해석을 하는 데에서 랜덤리스가 필요한 거고요, 기본적으로는.
네. 감사합니다. 토론을 해주셔서 시간을 이렇게 딱 채워주셔서. 네. 발표해주신 하크 애슐라. 네, 큰 박수 부탁드리겠습니다. 네, 본 세션은 이걸로 마치도록 하겠습니다. 수고하셨습니다.
수고하셨습니다.
No, I don't.